Hello everyone, my name is Candace. Recently, I did a machine learning project of hepatocellular carcinoma. So the dataset consists of more than 150 patients' data, and all the patients' data come from the clinical information, the demographics, the risk factor, and also some of the molecular information collected by a hospital in Portugal. So let's get started. The whole presentation will basically be divided into 7 parts. The first part is I'll talk about why I do this project. In the second part, I will talk about an overview of the dataset and its sources. And what the overview of the dataset means, I will explore some of the features with you guys, and I will also talk about what kind of features are included in the dataset. And I will also look at the class of the data of the different features, such as to see if they are character, integer, or numeric. So in the third part of the presentation, I will also do a little bit of preliminary exploration of dataset. So that means I will look at if there's any collinearity between different features, and also look at the mean mode median of the numerical features. And the fourth part is basically one of the major parts of the project, is about how I impute the missing values of the datasets. And the fifth part of this project is about machine learning models and also the results interpretation. I've applied several machine learning algorithms into this project, and I will also to go through with you guys. And the sixth part of this project is I will evaluate and compare the stack ensemble model. Now we can take it into R, and then we can also put in all the column names, and we can also look at the structure of the data. And there are 165 observations and 50 variables, and the last variable, the class, is basically telling us whether the patient is still alive or whether they're already dead. So there is like a gender feature here. If I want to see how many people are male and how many people are female, I can actually prop up like a table and to see the distribution of females and males. And if I want to see the features in a graph, and I can also put in like a histogram and to look at the number of nodules. So let's move on. And I also want to detect if there are any outliers in the dataset. So I've designed like a for loop, and the for loop will loop through the columns and then to see if there are any outliers. So the way that I define the outliers is the numerical values that lies beyond 3 standard deviation from the mean value of that variable. And since column 18, 26, 47 to 49 has more than 30% records missing, so for the following analysis, I will just exclude all this column because they have too many missing values. And the way that I impute the missing value is based on 2 algorithms. So the first one is I use KNN to impute all the categorical variables, and I will use median to impute all the numerical and also integer variables. So this function is basically doing the imputation of the numerical variables. I'm trying to impute the missing values with their median. And this function is it's the same. It's like imputing the median to any numerical data. And we can also run it here. And after that, you can see that there is no more missing values among column 23 to 44, and from columns 23 to 44, they are all numerical values. And later on, I will also apply the dummy variables on the categorical variables. So here is the performance status. So within this performance status column, there are PS0, PS1, PS2. That means the patients all show different performance status. And in that case, I will encode a dummy variable for this feature, because this feature is not supposed to be numerical and it's not supposed to be like a 0 and 1 yes no situation. So I will impute all these dummy variables, and that is also the same case for the other kind of ordinal variables. And later on, I'm here to impute the missing values contain the missing values of columns that are containing the categorical variables. And this function is basically imputing all the categorical variables. And you can see that after I apply this function on the columns, there are no more missing values. And later on, I will combine everything into one data set, and I will use this data set for our later on analysis. And I am also doing like a correlation analysis to see if different variables are showing any kinds of relationships. But we can see that a lot of the relationships are very close to zero, so which means the VHS may not share very strong relationships, or they are just like sharing very weak relationships. The next step, I will talk about how I apply the different kinds of machine learning algorithms in a data set. So one of the methods that I apply is regression methods. So here we can actually look at the logistic regression results. So this is the logistic regression results. You can see that there are not a lot of variables that are significant. So in that case, I want to improve the model by applying like a backward elimination. We can actually see the results in here, and then I will apply this formula into another model, and then we can see the summary of the model. We can see that in here actually a lot of variables become more significant, and our model will be better after we perform the stepwise backward elimination. And I also do a little bit of tuning to the dataset, and then this is a data frame that I use for the tuning, and this is automatic tuning. And then let's see the results. The results over here. And after I apply the tuning, the accuracy increased up to like 89%, which is really good. And then the 95% confidence interval ranges from 83% to 93%, which is also very good. And the sensitivity and the specificity also very high, so that means this model is running very well, and it can accurately predict a lot of changes in the life or death in the class variables. So the next data modeling algorithms that applies regression tree, and we can also see the results in here. So in the root node, we have 132 variables that are considering, and then here is the tree. And one of the advantages of the regression tree is because is that it is easy to interpret the results. We can see all the significance variables that are identified by this model, and then we can actually use this kind of features to determine if the patient is going to leave the disease or is going to die from the disease. And we can actually visualize the regression tree as well. So this will be a regression tree. I'd like to talk about the neural network. And in this case, we have to split the dataset into two datasets. The first one is the training dataset, and the second one is the test dataset. So the training dataset occupies 80% of the original dataset, and the test dataset occupies the 20%. So, but after we split the dataset into two parts, we want to make sure that the distribution of the class are more or less the same within these two datasets, so that our analysis can be accurate. And we can see that the zero actually like 38%, and for the other data sets like 36%. They're very close to each other, so we can keep going. And now we have to train the model, and the result is very long. But after we train the model, we want to apply the training model on the data set, and here's the result of it. And we can see that the data set, the model actually can accurately classify 67% of the values, and 33% of the values are classified wrongly. But in this case, I would also say that the model is doing a very good job. And here, this graph is basically showing what which variables are the most significant in determine whether the patient is going to live or is going to die. So here we can see that the importance, these few values has a very high importance bar in here. So we may want to take a look at it, or the physicians may want to take more consideration in these kind of variables when they want to estimate the patient is going to live the disease or die from the disease. And I want to do the neural network again, but this time I'm using a different package. So this time I'm using the neural net package that is we always use in the class, and we also have to train a model, and then to split the dataset into training and the test dataset, and then we have to apply the model. And this is the formula of the training model. And after that, we can also plot a model, but we can see that there are a lot of variables, so that's why it's like there are a lot of hidden layers in between. And then we also want to evaluate the models, and the correlation between the prediction and also the testing set is here. So the data set is only like 0.08, which means the model performs very weakly. So if I were to create a neural network, I would use the first model created by the NNet method instead of this neural net method. And the other algorithm that applies to a knife base, so I was using E1071 package to do this data modeling. And then again, I split the dataset into training and test and create the training labels and then to train the model of it. So this is basically I apply the train model into the test dataset to generate a set of like prediction. And then I also use a cross table to see the results of it. So we can see that actually the model performs much better this time. On top of the knife-based model that we have already built, I also applied the hold-on method without the k-fold validation on the knife-based model to see what happens. So we can actually look at the results here, and then we can also plug in a cross table, and then if we can see that the model is actually doing a very good job. Out of 40 cases, it's basically correctly classifying 27 of the cases. Next, we can also perform a tenfold cross-validation on the dataset. So here's the function of the tenfold cross-validation. And then here's the results. So the result is basically saying that the cap statistic is fairly low, which is only 17%. I would say that we can correspond to fair on the interpretation scale, meaning that the model only performs only slightly better than a random guess. And later on, we can actually use like a stacked ensemble model to see if a stacked ensemble model will perform better. And the first algorithm that we can use is bagging. I will also perform a 10K validation on the bag trees. And here's the algorithm of the bag trees. The bag trees can correctly identify 71% of the cases. So I would say that the bag tree is performed much better than most of the algorithms that we did before. The second ensemble model that applies boosting. So boosting is a little bit different from the bagging that we used before. Boosting focuses on the weaker variables that we identify in the previous training set, and then we put more emphasis on it. Here we can see the results of the boosting algorithm. The boosting algorithm can actually identify most of the cases correctly, but this is actually like a result of overfitting. And in order to avoid this error of overfitting, we want to apply the tenfold cross-validation on our dataset. And after we apply the tenfold cross-validation, and the model can accurately classify 73% of the cases. So the accuracy is also much higher than most of the algorithms that we've used before, such as knife-based or regression tree. And we will use kappa statistics to evaluate the model performance. And here we can see that this kappa statistic is about 0.33, which means the boosting model is a very good performing one. And the third ensemble model, which is random forest, also did a very good job. And here it says that the random forest included 500 trees here, and at each split there are 7 variables that are tried. Next, we want to evaluate the random forest performance by performing a 10K cross-validation. So here I am performing a 10K cross-validation on the random forest algorithm. And I will apply the random forest algorithm and use a kappa metric to select the best model. And after that, I will compare the results of the 10K cross-validation model, cross-validation of the random forest model with the boosted decision tree. And here we can actually see both the results of the algorithms. So basically what here it says that is like with a kappa statistics of 0.37, the random forest model actually achieves a higher accuracy than a C5.0 decision tree. The kappa values of the random forest model is higher than the decision tree, higher than that of the back trees, and more or less the same as the boosting algorithm. So therefore, I would consider both the random forest model and the boosting models to be the models that we should consider using in the future to consider this kind of data sets.